Okay, so today we're going to be going over Dalton's law of partial pressures and something called mole fraction. We're going to start off with Dalton's law, and I think you'll find it fairly easy. So if you have a mixture of gases, they're not reacting together and breaking bonds and making something new. They just exist in the same container and they are mixing, not reacting. Then what you can do is you can find the total pressure by just adding up the pressure of all of those gases. So each gas, let's say in this example, there's 3 of them. Each gas has its individual pressure, right? So every gas may have the same number of moles. They may have different number of moles, but those moles are exerting a pressure. And so if I just add up all the pressures, you can get the total pressure of your mixture. You just have to make sure that they're all in the same unit. This ellipses at the end just means do it for every single gas in the mixture. So if you had a container with 10 different gases, you have to add up 10 different pressures. 3 different gases, 3 different pressures. And so the gases are usually going to be things that aren't going to react. So maybe like noble gases mixed together, inert gases into helium, things like that. So they're going to behave independently. They're going to have their own pressure. And so if you add them all up, we'll get the total pressure, right? So here's your first example. A container holds oxygen at 300 millimeters of mercury. So that's pressure right there. Nitrogen at 500 millimeters of mercury, and carbon dioxide at 200 millimeters of mercury. What's the total pressure? So using this formula, let's just add them up. The first thing I would just check is, okay, are their pressure units the same? And they are. So whatever they're in, that's what our total pressure, the unit, will be as well. So our total pressure would be 300 millimeters of mercury plus 500 millimeters of mercury plus 200 millimeters of mercury. So our total pressure is 1,000 millimeters of mercury. And that's it. So fairly easy. The way they could take it like slightly more challenging right now, from what we know, is maybe a question like the next one. So you have a sealed container. It's a mixture. You have oxygen, nitrogen, carbon dioxide, and look at their pressures. All right, so it looks like, hey, let's just add them up and we can get the total. But here's the trick, if you will. It's asking about torr. So I'm going to pause the video. You should too. I want you to take a second, translate them all to torr, and then use your new formula to add them up and get your pressure. And come back here and check. All right, so right here you can see how I converted each of them to torr. It's not something you have to memorize. You should have gone back to this first page and you would have seen, okay, 1 ATM is 760 torr. So I had to put ATM on the bottom for each one to cancel them out, and your 760 torr on top. And I got these 3 answers. And so those are the partial pressures. We would call those a partial pressure of oxygen. It's the pressure coming from nitrogen, and it's the pressure coming from carbon dioxide. So those are your partial pressures. Add them together, and y'all should have got 722,000 torr. And so our last example before we move on to mole fractions down here, you have a closed flask. Helium exerts this pressure of 0.75 atm. Argon exerts a pressure of 1.2 atm. And then a third gas is added, and the total pressure rises to this. So what's the pressure exerted by the third gas? And so again, we're going to use that same formula. So total pressure would normally be the pressure of helium plus the pressure of argon plus the pressure of our unknown gas. I'll just call it X, right? I don't know what it is. And so in the 2 questions before, we were looking for this, but now we're just looking for this. So I'm just checking their units, ATM, 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 making sure we're all good there. So I'm going to plug in 2.30 here. For helium, I'm plugging in 0.75. For argon, I'm plugging in 1.20. And then I would solve for the pressure of X, right? And so you would do 2.3 minus 0.75 minus 1.0, and pressure of X would be 0.35 atm. All 3 of these problems are called Dalton's law of partial pressures. Partial pressure is the pressure of a gas in a mixture. Add them up to get your total pressure. And we're going to use this formula in the next page, but we're going to calculate something new. It's called mole fraction. I like to think of mole fraction as very similar to a percentage. So out of your mixture, what percent of it is coming from each individual gas? I'm actually going to start with this formula in the center, and I'll go right back up to the top. But in the center, this X stands for mole fraction. And so the I underneath it is usually where you would put your gas. So if it was nitrogen, that would be X into carbon dioxide, X CO2. So that's all that stands for. And so if you look over here, this is the moles of the gas that you are trying to find mole fraction for. And on the denominator is your total moles in your mixture. So all the moles in the mixture. And so that's why I think it's kind of similar to a percentage. It's kind of letting you know out of all the moles, this much is coming from each particular gas. And so once you get that, you leave it as a decimal. There is no like multiplying by 100, okay? And so that's called mole fraction. And so what you can do with that is you can say, okay, if I got 0.8 here, let's just pretend. That's about 80% of my gas is coming from this one, 80% of my mixture is coming from this one gas. So I could also say 80% times the total pressure will give me the pressure of that gas. And so I'm just taking my mole fraction, the percentage of moles that I have in there, and I'm multiplying it by total pressure, and that will tell me my pressure of an individual gas, which is also called partial pressure. So when you have a mole fraction, there are no units. If you find the mole fraction of every gas in your mixture, then they should always add up to 1, because just like percentages add up to 100, we're not turning them into, we're not multiplying them by 100, so they're all going to be decimals. They should add up to 1. So let's look down at the bottom. A mixture has 2 moles of helium, 3 moles of neon, 1 mole of argon. What's the mole fraction of each gas? So we have to do this 3 times. I'm going to do the first one, and then you can pause it and do the next 2, and then we'll come back and do letter B. So let's say I want to know mole fraction of helium. Okay. On my numerator, I would just put moles of helium. Well, how many moles of helium do I have? 2. But on my denominator, I have to put all the moles. So that would be 2 plus 3. I'm getting the 3 from right here. Plus 1. Right? So it's just like 2 over 6. Because 2 plus 3 is 5. Plus 1. And you do not multiply it by 100. So when you get your decimal 0.3 repeating, that is your mole fraction. I'm not going to put any units behind it. So the mole fraction of helium is 0.33. Now, let's go ahead and do neon. The mole fraction should be bigger because I have more moles. Let's do argon. The mole fraction should be smaller because I have less moles. And then you can always check yourself. Add them up, see if they equal something really close to 1. So pause it and try those 2 out. Okay, so for neon, your numerator should be 3 and your denominator shouldn't change. We're in the same mixture. So our mole fraction for neon is 0.5. So that means half of the pressure is coming from neon because it has the most moles. For argon, it should have been 1 over 6, and so you're getting 0.16 repeating, so I rounded it off. And just if you wanted to check yourself, you add them up. We're getting something really, really close to 1. The reason it's not exactly 1 is because I had around that repeating 3 and that repeating 6, so I would be happy if I got something like that. Now if we look at B, it says if the total pressure is 720 millimeters of mercury, what's the pressure of each gas? So if I want to know, okay, well, what's the pressure of helium? I would take helium's mole fraction and I would multiply it by the total pressure. So the mole fraction of helium we just found, 0.33. And then the total pressure they gave us. Since the total pressure is in millimeters of mercury, my answer is going to be in millimeters of mercury. So 0.33 times 720 millimeters of mercury is 237.6 millimeters of mercury. And so you can do that for each gas. So again, pause it, try it out for neon and argon. And then again, a good way to check yourself, if you add them all up, it should equal 720 because that's Dalton's law of partial pressure from the previous page. So here are 3 answers. And we would get a slightly larger number, like here, for example, if we kept more 3s. So when you add these up, you're going to get something really close to 720, but it might not be exact. And it's just because I'm shortening off my decimals where they were repeating. But for each one, I took the mole fraction that we found, I multiplied it by total pressure, and then I got the pressure of each individual gas, partial pressure of helium, neon, argon.